Hello and welcome to the Planet Cutting Edge Solutions tutorial on Object Tree. This video will take us through how to utilize Object Tree to apply equations to parts that allows us to build parametric cabinets. A parametric assembly or cabinet is able to be sized with all the internal parts and components staying in the correct desired position. By default, all standard cabinets, even those modified through Section Editor, will achieve this. The advantage of using Object Tree is being able to fully customize parts within an assembly, customizing its rotation, placement, and size. Object Tree is afforded to Solid Advanced and Solid Ultimate. The ability to apply equations to parts without Object Tree is also able to be achieved in Solid Drafter. This tutorial will be conducted in Solid Ultimate. Before we start, it is essential to understand the X, Y, and Z axis that objects are structured off. Listed in the description of this video is a link where you can find a visual guide on how to properly understand this in the context of cabinet vision. The X, Y, and Z of an object refers to its position, whilst the DX, DY, and DZ refers to its size. The first example we will investigate is enabling a top stretcher to rotate 90 degrees. Many users wish to achieve this when creating a sink cabinet, with the rotated rail making way for such things as plumbing or sink hardware. If we were to simply rotate an existing rail inside a job, it would look like this. This correctly achieves our result. However, if the cabinet is resized, the rotated rail does not correctly adjust with the cabinet. Here we can see a cabinet that has had the rail rotated without equations applied. The rail will not stretch with the height of the cabinet. The following shows the exact same cabinet with equations applied. The rail will now properly adjust with the cabinet. This is to highlight a basic example of what we will achieve with Object Tree. We will begin by opening a new job and placing a two-door cabinet. From the plan and elevation view, we can see that Object Tree appears in the Tools section of the ribbon bar. Opening Object Tree, we are now presented with a dialog box. This is what we refer to as Object Tree. We can see the room listed on the left-hand side, with parameters listed on the right. The Add, Edit, and Delete buttons will be of use as more parameters display above them. The navigation is as follows: Room, Wall 1, Front Face and/or Back Face. Since we have only placed objects on the wall's face, that is why it has child folders within it. We can now see the placed object, and within that, all parts are listed that make up our two-door base cabinet. Selecting a line will display a range of information on the right-hand side of Object Tree, with a code appearing also on the top line. If we now select an individual part, we can see its actual dimensions reflected as the D reference, and its placement as an X, Y, or Z value. After configuring our first cabinet, we will come back and utilize this information later on. Closing Object Tree, we will now double-click on our cabinet and enter the End view. Since I want to operate on the top stretcher, I will click on it from this view. Whenever we click on an area that is occupied by one or more parts, we are presented with a selection of choices. The list is populated by parts that occupy the space clicked. Parts of a similar type are grouped as this. The part furthest away is listed at the top, and the part closest to the viewing camera is down the bottom. Selecting Top Stretcher, we now see in the left-hand side that it is currently selected. We can now use the Rotate Part By box to add a rotation increment of 90 degrees. Now rotated, we can understand that this part's reference point, which is indicated by this dot, means that it rotates around this point, explaining its rotational movement. This part now needs to be moved in the Y plane to ensure it situates correctly in the cabinet. The Y placement is controlled in this box here. Something that helps us understand the X, Y and Z axes are these axis lines here. If I were to simply shift this part down in the Y plane as shown before, the second I increase the height of the cabinet, it would not move to the correct placement. This is where we need to change this Y value to an equation, so it will always correctly place its own width underneath the top cabinet height. I need to identify what values I need to grab: the cabinet height, or dy, and the top stretcher width, or the dx of the stretcher. This is because if the construction method ever redefines the width of my stretchers, I need to ensure that it will correctly reference its own width for the purpose of how it places itself in the Y plane. Now I take a look at the cabinet in the object tree. Since I have pressed the object tree button whilst having the cabinet selected, it will not display the room or wall values to the left. I have the whole cabinet selected and I can view its parameters on the right. I need its height, which is shown as the dy. So I can copy this code up here, which will be used for the Y or elevation of my top stretcher. Navigating back to my top stretcher, I will paste the copied code in the up-down field by clicking on the box and pressing the 3 dots shown here. This brings up the parameter edit for this part alone. Currently set to a static value, we will change it to an equation. It displays this: if 1, then 0. This essentially means if 1, which means yes, then 0. 0 being the equation we will create. So to summarize, it is saying if yes, then this equation will be achieved. I will paste our copied parameter into the then box. I can see what value the parameter that I just pasted will achieve by pressing test. The equation returned a result of 876 field. I will press OK to see this in a So the up/down box will display this logo, which tells the user that an equation is bound to that field. Since my part is still in the incorrect position, I will reduce the up, down or Y value by 80mm, or more correctly, the width or dx of the top stretcher. Pause the video now and see if you can navigate through Object Tree to find the correct parameter. Remember, you need to click on an individual item in Object Tree to display its given parameters. Okay, now I will find the dx of my top stretcher so that it may be used for a reference. I have selected the top stretcher and can see its parameters on the right. More importantly, I can see the dx value, so I will select it and copy the code shown above. Navigating back to the parameter edit for the top stretcher, I will now use the then box in addition to the already occurring cab.dy text to create a mathematical equation that will utilize the new parameter I have copied. Since the top stretcher is too high, I will type the equation as follows: cab.dy minus cab.case.ts or top stretcher.dx. This portion represents the cabinet dy or height, whilst this portion represents the width or dx of the top stretcher. Pressing test, we can see that true indicates that the value returned is 787mm. Pressing OK, we can advance out of the cabinet and the top stretcher has now conformed to the correct height, also listed in the top left up-down field. To further test if this works, stretch the cabinet height to ensure the part stays at the correct position. Also stretch the width and depth of the cabinet. What we can see is that despite only the Y position of the top stretcher having the proper equation applied, it conforms correctly to the sizing of the cabinet. This is because the part automatically had parameters applied to it when it was brought out from the cabinet library into the workspace. When we rotated the part, only the Y position was affected. Therefore, all other settings for that part stayed automatically tied to the cabinet. The instance where we would need to entirely create equations for all positions and D values or size of the part is if we added the part manually into a cabinet. We will now explore creating a shelf nailer for a fixed shelf. The second example we will explore is adding a new part to our assembly and using object tree to place it correctly. As mentioned in example 1, the following part will not be an existing assembly part. The size and placement parameters will need to be configured. This task is specifically designed to be an introduction to the workings of object tree and equations when adding new parts to cabinets. Starting with a blank cabinet in a job, we need to ensure that it has a fixed shelf placed internally. We will now enter the cabinet's face view and place a new part. I will categorize the part as a nailer on the left and press Next. The only size we will modify is the width. The length will be configured at a later stage. We will set the width to 50mm. This screen asks us for the orientation, so we will set it to the following. We will advance through the last step and press Finish. Now rotate the part using the Rotate Part By. Seeing the axis lines here, this is how we establish where the origin point of this part is. Also, utilize the link in the description to understand the origin points of parts better. We will first focus on the placement of the part, which is the X, Y, and Z values. I want to first set the Z value. Since this will align itself under the fixed shelf, we will see if there is an existing assembly part which I can use. From end view, we can establish that the fixed shelf, when clicked, has an origin at the location we want the nailer to place at. Like the last example of the rotated rail, we also need to accommodate for the width of the nailer. For the up/down of the nailer, my equations were as follows. Fixed shelf position from the bottom of the carcass plus toe height minus the 50mm width of the nailer. This is expressed as the highlighted code. My left/right needs to reference the shelf width as well as the unfinished end thickness to properly place horizontally. The equation is as follows. Left unfinished end thickness plus the dy value of the fixed shelf. The reason we always need to reference individual part parameters when constructing an equation is so that if material thicknesses and sizes change, our new part will accommodate. Now it is time to set the length of the part to change automatically. We can see from face view that it is too long, so we'll once again use object tree to construct an equation. Logically speaking, we always want the nailer to match the shelf length, so we can search through object tree for the parametric code that represents the fixed shelf length. Pasting the code into the length or dy of our nailer, it is now properly sized to the shelf. Make some adjustments in the width, height and depth of the cabinet and make sure that the nailer adjusts and places correctly. These have been two examples on how to utilize object tree to locate parameters and how to then copy the parametric codes to construct equations so your new or existing parts can modify themselves as you please. Thank you very much for watching this video on object tree, and please make sure to utilize the link in the description as well as other videos in our channel.